Right, let's have a look at the features and see how we're going to make this. The main feature appears to be the 60mm bore with an H8 fit. Since it's a tight fit, we're going to need to bore this. It would be best to rough it out using Helical milling. We have 3 tapped holes with an M10 1.5mm pitch. Right, that's not a problem. The TYP on this feature means typical. That means all the holes are 8.5mm unless otherwise stated. So we have 4 holes, that's 8.5. This works out well for us because 8.5 is also the tapping drill size for our M10 tapped holes. The quotation marks on the bottom here mean equal equal. This means both lengths are exactly the same size. So our overall length is 260mm, that makes these 130mm each. It is written like this purely because draftsmen are the most laziest people on the planet. The centre line of this row of holes are all 15mm from the bottom edge. So looking over this drawing, I think we have 2 options for our datum position. One is in the centre of the major bore, as it's a big feature and it has to be accurate, or the other one would be the bottom left hand corner where most of the dimensions run from. But since there's not a note on the drawing saying that all dimensions must run from the centre bore, we're going to use the bottom left hand corner datum. There's a few ways we can engineer this to decide how we're going to machine it and in what order we're going to cut. One way would be to drill and tap the 3 tapped holes first, and then use that to locate and screw into a backplate to machine the rest of the component. But to cover all the lessons in the course, I'm going to machine it like this. First, I will use a slot drill to rough out the major bore in the centre. Then, using the boring bar, I will finish bore it to the H8 dimensions. Following that, I will then cut the profile out. We are assuming the billet is already 20mm thick, so we don't need to block it up before we start machining. Once the profile has been cut out and the centre bore is in place and accurate, we can then use clamps to locate it on a different fixture with a datum shift so we can machine the rest of the holes. There is many different ways we can machine this, but the order I have decided on enables us to use every operation that we've discussed in this series of lessons. So let's start writing our program. The first thing we need to do is lay out our header information. This makes it easier for the operator to know what tools we're using and in what order it will be cutting. So the first line is we add our program number and an operator's note telling the operator what the program is called. This operator's note also shows up on the controls, so it's easy to identify when looking through the programs inside the machine. Now we add information about who programs the part and also the date, but please note there is no way I would work on January the 1st, New Year's Day, ever. Now I'll make a note of what machine this part was meant for when I programmed it. If this is loaded to a different machine, all my datum shifts will be in a different place. Under that, we put the line tooling to identify that we're now going to list the tools that we're going to be using for this component. Using the N numbers as search numbers, I tell the operator which number to search for to find this block of code. Tool 1 is our tool number, and 01, the following number, is for our offset. So T0101 is tool 1, offset 1, followed by an operator's note of which cutter I am using. This helps the operator not only know what tools the machine uses on this program in advance at the beginning of the header, but also gives him a reference when he's searching into different blocks of the code to rerun certain parts of the program. I then go ahead and fill out tooling information for each tool that I'm using and in the order that I am going to be using them. Assuming I know where our datum positions will be by using a touch probe or clocking them in, I now define their locations using the G10 command to set the datum. The P1 value sets this particular datum into the G54 datum position. The X, Y and Z is the position of the datum within inside the machine as reference to the machine datum. The machine datum is normally referred to as G53. We can also return to the machine datum by using a G code G28. I will discuss a bit more about that later. Since I'm going to be using a second fixture when we clamp through the bore and then drill the holes, I set a different datum by using a separate G10 command. This time we use P2 to tell the machine to put the datum into the G55 position. The XYZ coordinates are the datum location. Right, let's remove the header information from the screen to make things clearer for us to see, and we can start programming our part. The first thing we need to do is bring in our tool, add a search number N1, and define our tool with T0101. Then an operator's note in brackets telling the operator what tool we are using. The M code M06 does an automated tool change, bringing our tool into the spindle. This line of G codes is often referred to as the safety line. The idea is, as we call in any tool, we add this line underneath. It puts the machine in a certain state, so it's always safe to run from the position of any tool. This is so we can jump back in the program and run a tool in any order we wish, without having to worry about the machine being in the wrong modes. So let's go over what this line includes. The G90 sets the machine into the absolute positioning system. The alternative for this would be G91, the incremental system. G54 sets our first datum. We are using two datums during this component, G54 and G55. In this case, we need a datum on the bottom left hand corner of this material when it's in this fixture, so we're using G54. G21 sets the machine into the metric measuring system. The alternative would be G20, which is the imperial system. G17 selects which working plane we are working on. We're currently working on the X and Y plane, so we use G17 to set this. G80 cancels any cycles that may be active. If we had to stop the machine in the middle of a cycle, the machine reading this line will cancel that cycle, so it's safe to run. And finally, G43 is our cutter compensation offset. The machine will read the cutter compensation from the tool table in the machine, so no value needs to be added after this. Here we set our spindle speed. The S value is the speed of our spindle, and we're using 1000 revs per minute. So S1000 is 1000 revs per minute. M03 turns our spindle on in a clockwise direction. Now we need to rapid our cutter to the start position of our bore. So using G00, the rapid travel command, I move X 101mm and Y 60. How do I come across the 101mm? Well, the width of the component is 260mm. The centre line of the bore is in the centre of the component at 130mm. The radius of the bore is 30mm, so that gives us 100mm. Now I'm wishing to leave some material on this bore because we're going to finish bore it with a boring bar later. Because of that, I've offset the cutter 1mm to the right. Still in rapid mode, I now bring the cutter down to 1mm off the surface of the material using Z1. The M08 command turns the coolant on. Switching over to our feed rate command of G01, I bring the cutter down to minus 0.1mm into the component with a feed rate of 200. Now we can start our Helical milling. G03 rotates the cutter around the centre point in an anti-clockwise direction. Our X and Y positions are the end point of this arc. Z is the depth of cut we are taking during this movement, and R29 defines the radius. This is a 60mm bore, but we're using a 29mm radius at this point because we wish to leave material on for the boring operation. On this line, we bring the cutter back to the start position using G03, but at the same time bringing the cutter down 2mm more as a depth of cut. From here on, it's just a case of copying the same lines again, but adding to the Z depth each time. This is where having a machine that can copy paste or programming offline is beneficial. We return to our start position while adding 2mm to our depth of cut. We continue this until we reach a depth of 22mm, which brings the cutter 2mm below the bottom of the material. Because we don't want to drag our slot drill up the side of the material of the bore, we offset it to the centre line of the bore using G00 X130. This way we can wrap it away from the bore without touching material. Still operating under the rapid mode of G00, add Z50 movement to bring the cutter 50mm above the face of the material. M09 turns off our coolant. G53 is our machine datum, so returning to X0Y0Z0 on the G53 takes our tool back to the tool change position. An alternative for this would be using G28, which is a reference return point G code. It operates much the same way, and M05 stops our cutter from rotating. G40 turns off our cutter compensation. And finally we have M01, which is our optional stop M code. The operator has a choice of whether the machine stops at this point, so we can measure the job or check the condition of the tools. This is done by pushing the optional stop button on the controls, and the machine will stop every time it reaches an M01 value. And that concludes the operation of roughing out our bore. To continue this lesson, which includes finish boring the large hole, centre drilling the holes, peck drilling the holes and tapping, and also cutting out the profile using G01 and G02, head over to my website where the course is hosted, and it's totally free.